Hello lovelies, in this video we're going to be going through OCR Gateway Separate Science Foundation Physics Paper 1, the paper that we've written for 2024. So what we want you to do is to pause after each question comes up, have a go at it yourself on a bit of paper, and then play and watch us work through that one.
You are asked to select the value for the typical diameter of an atom. Now this is a recall question, so if you're wondering how you're meant to know this, examiner simply expects you just to know it. However, as this is a multiple choice question, we can narrow down our options. We know that atoms are very small, and therefore they won't have a positive power in standard form, because that's used for big numbers. That leaves us with 1 times 10 to the minus 5 or 1 times 10 to the minus 10. Now atoms are actually really small. So they are in fact of the order of 1 times 10 to the minus 10. Now, as this is a fact that we need to know, this is the perfect opportunity, if you don't know this, to get out your notes, to get out a flashcard, write on one side of that flashcard what is the typical diameter of an atom, and on the other side of it write 1 times 10 to the minus 10 meters, and then you're guaranteed to get this right next time. A force of 32 newtons is applied to a spring. The spring stretched and had an extension of 5 centimetres. Now we're asked to calculate the spring constant. So to be able to answer this, we need to know the equation. We should know that the force exerted by a spring is going to be equal to the extension multiplied through by the spring constant. So that's our equation that we're going to use here. Now if we look through the information that we've been given, you can see we've been told the force that's exerted by the spring, that is equal to 32 newtons. And we know the extension is 5 centimetres. This is where our first problem pops up here. Remember that in physics we use metres, we don't use centimetres. So in this case we need to convert the extension from 5 centimetres to metres. And we do that simply by dividing through by 100. So extension here that we're going to use is 0.05. So if we look at the question, you can see we're being asked to find the spring constant. So that means that as this isn't already the subject of this equation, we need to rearrange the equation. Spring constant therefore will be equal to that force divided by the extension. So if we now substitute in the relevant numbers, we'll get 32 divided by 0.05. And that gives us an answer equal to 640 Newton per meters. And of course, that is our answer. So A is our answer. So we'll put in our box A. A 0.1 kilogram block of ice was melted. We're told here that the specific latent heat of fusion of water is 330 kilojoules per kilogram, and we're asked to calculate how much energy is required to melt the 0.1 kilogram block of ice. So first things first here is we need to identify what equation we need. We're talking about specific latent heat in this question, and we only have one equation in physics that we're going to use for that. And that is that the change in thermal energy is equal to the mass times by the specific latent heat. So there is our equation there. Now the energy that we're being asked to find is going to be that change in thermal energy. Now looking at what they've given us, I can see they've given me the specific latent heat, in this case of fusion. However, they've given it as 330 kilojoules per kilogram. Now this is really sneaky here, because we need it to be in joules per kilogram, not kilojoules per kilogram. So to convert from kilojoules to joules, we times through by 1000. So that gives us 330,000 joules per kilogram. So there we go, we've got that now. We also know that the mass is simply 0.1 kilogram. That is in our standard units for mass, so we're happy with that. So now we're going to have 0.1 times by 330,000. And that leaves us with our energy of 33,000 joules. And looking at the answer options, I can see that B is 33,000 joules So I'm going to write B in my answer box. You can see there though that if you miss the fact that it was kilojoules per kilogram, then we would get a completely different answer. So please do be so careful of the units in physics. It's almost like they're being really sneaky and trying to trip you up, so don't fall into that little pitfall. Identify the scalar quantity in the following options. So here we've got velocity, acceleration, distance and displacement. Now this is just a fact recall question. We just need to know which of these are vectors and which are scalars. Velocity is of course a vector. Acceleration is also a vector because we can accelerate and decelerate. However, distance is a scalar. Displacement is the vector version of distance. However, distance is the scalar. So our answer here is C. Just to remind you before we go on to the next question, the difference between a vector and a scalar is that a vector shows magnitude or size and direction, whereas a scalar just shows that magnitude. It doesn't tell you which direction we're going in, or if it's negative or positive, for instance. So distance is the scalar version of displacement. We just know how far we've gone, not whether we've gone left, right, up or down. Two people, A and B, sat on either side of a seesaw. Person A has a weight of 600 newtons. So let's draw that on then. We've got this downward force at A of 600 newtons. We're told that the seesaw was in equilibrium, and we're asked to calculate the weight of person B. Now, the important thing here is that the seesaw is in equilibrium. That means that the clockwise moments are equal to the anti-clockwise moments. Let's remind ourselves of the equation for a moment of a force. So the moment of a force is equal to the force times by the distance from the pivot to that force. And that distance always needs to be at right angles to the force. So now we've reminded ourselves of what the equation for the moment of a force is, let's write down that rule that we mentioned that the equilibrium fact tells us. So we know that the sum of all of the clockwise moments is going to be equal to the sum of all of the anti-clockwise moments. So now that we know this rule, what we need to do is to have a good look at our diagram and work out which forces are going to cause clockwise moments and which forces will cause anti-clockwise moments. So let's start by looking at B. So B has a weight as well. And imagine around that pivot, what's going to happen is the seesaw is going to go around in a clockwise direction. Whereas the person at A, again, if you think of that seesaw, it's going to go down, which is effectively moving in an anti-clockwise direction. If we work out the moments of each, so the anti-clockwise moments are 600 times by 1.4, and that's equal to the clockwise moments, which will be B times by 0.8. Now, rearranging this, I can find out what B is now by dividing by that 0.8. So B is 600 times 1.4 divided by 0.8, which gives us 1,050 newtons, which is going to be the weight of person B. A current of 0.1 amps passes through a 20 kilo ohm resistor. Here we're asked to calculate the power dissipated. So first things first, let's have a think about what we know already so we can work out our equation. We know that we need to find the power, we're given a current, and we're given a resistance. That means if we look through the equations that we know, we can use the one that states that power equals current squared times by resistance. Now we know current is equal to 0.1 amps, whereas resistance is 20 kilo ohms. However, we've got that problem again of how in physics, we don't want things as kilo or whatever, we just want ohms in this case. So we need to convert the 20 kilo ohms to ohms by just timesing through by 1000. So that means we have a resistance equal to 20,000 ohms. Plugging these numbers in now to our equation, we find that power equals 0.1 squared times by 20,000. Now popping that into a calculator, I get 200 watts. So our answer here will be D, 200 watts. The diagram below shows the electric field pattern between two charges X and Y. Here we're asked to identify the correct charges for X and Y. And to do this, the fact that we really need to know is that electric fields move from positive to negative charges. So when we see the direction of these arrows here, we can see that it's moving away from X, but it's moving towards Y. Now that tells us that X has to be X, so we can cross out the negative options, and that Y has to be negative. And so as a result, our answer must be C. So C is our answer, and it is that simple. We just need to use the fact electric fields go in the direction from positive to negative charges. Component X was connected to a circuit. As the temperature was changed, the resistance also changed. The relationship between temperature and resistance is shown on the graph below. And here you can see that as the temperature gets bigger, the resistance gets smaller. Now this must mean that we have some sort of a temperature-dependent resistor. So we need to remember what the name of a temperature-dependent resistor is. And looking at these options, it is the thermistor D. So D is our answer. I always remember the ister part of the name is coming from the fact it's a resistor. And the therm bit, just like a thermometer or thermals, it's to do with temperature and heat. So really, when you understand what those parts of the word mean, it's really obvious that this is a thermistor. Here we're asked to identify the circuit symbol for a variable resistor. So we should know these all off by heart, but I'll tell you what they all are. Well, first off, the variable resistor is the resistor at position A. Okay, so that is the correct answer to this question. Here we have a variable resistor, and that is what we put in our answer box. But let me tell you what the others are as well. Okay. In position B, this circle with an A in it is an ammeter. We should know that an ammeter is used to measure current. Next up, in C, we have a resistor. Generally in physics, whenever we have a rectangle as part of the circuit symbol, it is some type of resistor. If you look above, you can see the variable resistor had that rectangle too, but the arrow told us that it was a variable resistor. And finally here, we have a rectangle with a circle around it, although you may also see it without the circle, and two arrows going towards the resistor. So this is going to be a light-dependent resistor. So the fact that those arrows move towards it tell us that it is light-dependent, and the fact that it's a rectangle tells us that it's a resistor. So that's what those circuit symbols all mean, but the answer to this one is A. We've got a 1000 watt television watched for 6 hours. Here we're asked to calculate the energy transferred, and notice all of these energies aren't in the standard joules, they're in kilowatt hours. So that means that when we find an equation for this, we need to keep the units in kilowatts and hours to get these kilowatt hours. So let's find the equation we need. We need energy transferred, we need power, which is the watts, and time, which is the hours. So here we have energy transferred equals power times time. That's the equation we need for this. But like we said, because the energy needs to be in kilowatt hours, our power needs to be in kilowatts, and our time has to be in hours. Now this is a very rare time when we're going to convert away from the watts that we're given into a different unit, in this case kilowatts. So 1000 watts is equal to 1 kilowatt. We get that just by dividing through by 1000. Whereas the time is 6 hours, and that is what we want. So here we're going to do 1 for the power times by 6, which gives us 6 kilowatt hours. So our answer to this one is A, 6 kilowatt hours. A person weighs 700 newtons on Earth. We're told that on Earth the gravitational field constant is 10 newtons per kilogram, and on the Moon the gravitational field constant is 1.6 newtons per kilogram. Here we're asked to use this information to calculate the weight of this person on the Moon. So there's a little bit going on here that we need to think about. It's not an easy question this, there's going to be a couple of different steps. The first thing we need to do first is just identify what equation is going to be relevant. I want us to use the equation that weight is equal to mass times by gravitational field strength. Now, you may be more familiar with this, instead of it saying weight, as saying gravitational force is equal to mass times by the gravitational field strength. They are exactly the same because, of course, the weight of an object is its force due to gravity. So let's have a look at the information we know about Earth. We know the person weighs 700 newtons on Earth, and therefore that is their gravitational force. We also know the gravitational field strength is equal to 10 on Earth. So that means that we've got enough information to work out the mass of this person. And the mass does not change whether we're on the Earth or the Moon, that stays the same. So that's the key to this question, finding the mass of this person and then using that to work out their weight on the Moon. Well, rearranging this equation, we find that mass is equal to the gravitational force divided by gravitational field strength, which gives us 700 over 10, which is 70 kilograms. So now we need to calculate their weight on the Moon. Here all we need to do is to plug in the numbers into our equation again. The mass is 70 because again, that's the same whether we're on the Moon, the Earth, anywhere. And we times it by 1.6. And that gives us 112 newtons for the weight of this person, which is option B. So that is all we need to write to get our answer. The circuit diagrams below show 4 different arrangements of identical resistors. Identify which arrangement has the highest resistance. Now, what's really important for us to know here is that when we place resistors in parallel, what we do is we reduce the overall resistance. They're less actually then than the individual resistances. And that's because you've given this current more options as to where it can flow. Therefore, in B, C, and D, in each of these, we have parts of it that have parallel regions. In B, you can see that all of it is parallel. In C, you've got this chunk in parallel. And in D, you've got these 2 regions which are parallel. The only one out of all of these that doesn't have any parallel regions is A, which simply has 3 resistors in series. Now, as a result of this, the arrangement with the highest resistance is going to be A, because it is just in series, no parallel regions, and therefore we just add up those resistors to get the total resistance. So A is our answer. Miles per hour is a commonly used unit of speed. In physics, SI units are used. The SI unit for speed is meters per second. Here we're asked to identify which of the following speeds is approximately equal to 60 miles per hour. And we're told that 1 mile is equal to 1,609 meters. Now, by converting units like this, I like to think of it as 60 miles per, so divided by 1 hour. So we need this in meters per second. So what we need to do is to convert the 60 miles to meters and convert the 1 hour to seconds. Well, we're told that 1 mile is equal to 1,609 meters. To get 60 miles then, all we need to do is to take this 1,609 and times it by 60. That gives us 96,540. And that's how many meters 60 miles is. Now let's convert the hour to seconds. So there's 60 minutes in an hour and 60 seconds in each of those minutes. So that means 60 times 60 is the number of seconds in an hour, and that's 3,600. So 96,540 divided by 3,600 gives us 26.8 meters per second, which of course, out of all of these options here, the closest one is going to be 27. So A is our answer. Now we need to identify the row that has the correct units of power and energy. So this question really relies on our memory, okay? We need to know what units we measure power in and what units we measure energy in. So power is measured in watts. So B is looking like the answer here. Let's also just reflect on what the unit for energy is. Energy can actually be measured in either joules or kilowatt hours. Both of those are acceptable units for energy. However, here you can see that only B is correct for both the power and the energy, and therefore our answer to this one is B. Identify which of the statements defines Newton's third law. So we need to know which of these is the definition that fits. So Newton's third law states that when two bodies interact with each other, the forces they exert on each other are opposite and equal. So the answer to this one is indeed A. That is the only definition that fits our definition for Newton's third law. So that is our answer, A. And if you didn't know what Newton's third law was, then this is the perfect opportunity just to take a moment and write that down on a flashcard and go away and get learning it. The graph below shows the heating curve for water. It shows how the temperature of water changes as the energy absorbed increases. We're asked in this question to write down the value of A, which is the temperature. So to answer this, let's just evaluate this diagram, okay? So you can see that X is found at negative temperatures. And because it's negative temperatures, it means it's very cold. Now that to me tells me that X is actually ice or solid water. Y therefore is going to be liquid water, and Z is going to be gaseous water or steam. So by recognising those different states, we can see that it's when Y changes to a gas, that's the temperature that we're looking for. And we should be familiar with the fact that water boils and changes to gas at 100 degrees C. Here we're asked to explain what the horizontal regions on the graph show us. So I've included this diagram here for us to look at. So here are the horizontal regions we're being asked about. Now notice that those horizontal regions, the temperature is constant. The temperature isn't increasing at all at those points. The reason why the temperature is constant here is because these are the points where we get changes in state. And in these cases, all of the energy being inputted is being used to break the bonds between the particles. So that means that the energy isn't being used to increase the speed of the particles and therefore their temperature. All of the energy is being used to overcome those intermolecular forces. Now, this question here is a 2-mark question. So to be able to get those 2 marks, we need to state 2 key points. I think the most important of all these options is the fact that there are changes in state. We should just understand that of the horizontal regions. But then any explanation as to why the temperature doesn't increase would be your second point. So either you could state that the energy being used to break the bonds between the particles, or we could say that their energy is not being used to increase the temperature. Either of those can get you your second mark. So now we're told that the water is in different states at points X, Y and Z on the graph. So now we're asked to draw a line from each box to show the arrangement of molecules in X, Y and Z. So what we need to do is to recognise what state X is, what state Y is, and what state Z is. Now, because Z is going to be the state that we have when we're at a very high temperature, we can see that this is going to be a gas. X is when the temperature is very cold, it's below 0. And we know that when water is below 0, it freezes. So that means that X is going to be a solid. And Y is the region that we're in when we've come above 0 degrees, we've warmed up, but before we're 100 degrees. And so Y is going to be a liquid. So that's the first thing that we need to do to answer this question. Now we need to recognise that when we're in the solid state, as we are with X, all of the particles have a regular arrangement and they are all next to each other. So this is what we have in X. We can see that they're in layers and they are all very close to each other in this regular arrangement. And that's what we would expect to see with a solid. So now let's have a think about the gas Z. We should know that when we're a gas, the particles are far apart, they're moving with high energy, and they're moving quickly in all directions. And so the one that most fits this, particularly looking at how far apart they are, would be Z going to this middle option here, where the particles are far apart from each other. Now Y now, we can clearly see, is going to have to be the other one, okay? But let's remember that Y is a liquid. The particles are close to each other, but they're not quite as close as they were when they were a solid. And they are moving around each other in a random arrangement. We still don't have that regular arrangement we have when we have a solid. And so Y is going to be this arrangement here. The density of solid water ice is 916.7 kilograms per metre cubed. Calculate the volume of a 2 kilogram block of ice. So this is a calculation question. We need to write down the equation that's relevant. Here we're being asked about density and volume. So that means we're going to use the equation that density is equal to mass over volume. I always like to lay out the information they give me in the question too. So I've written down what the density is and what the mass is so that it's nice and neat and tidy. So now we know density is mass over volume. Now we need to find the volume. Now to do this, we need to rearrange the equation. Now you may be super comfortable with that, but if you're not, remember you can use the triangle. In this case, the triangle has mass on the top and density times volume on the bottom. The way they work is we cover up what we're looking to find, in this case the volume, and look at the triangle to see what the formula will be. So because it's m over d, the volume is equal to mass over density. So that's equal to 2 over 916.7. So there we are now, we've got our calculation. We just need to put that into the calculator, and that gives me 2.18 times 10 to the minus 3. Or you could give it as 0.00218. There you are, that is question D. Here we're told that the specific heat capacity of water in state X, Y and Z is given in the table below. We're told that the specific latent heat of fusion for water is 334,000 joules per kilogram, and the specific latent heat of vaporization is 2,260,000 joules per kilogram. Here we're asked to complete the sentences to describe the difference between specific latent heat and specific heat capacity, and we're told we can use the words from the box to help us. Okay, so these are a pair of definitions that we really need to learn. And so if, when I tell you these definitions, you don't actually have them memorised, then this is the perfect model answer to put on some flashcards and just go away and get learning it. Okay, so let's look at this. Specific latent heat is the energy required to change the something of 1 kilogram of a substance. So latent heat is all about changing state. So that could be between going from solid to liquid or liquid to gas. But latent heat is always about changing the state. So that is our answer here. Then we're told that specific heat capacity is the energy required to the something of 1 kilogram of a substance by 1 degree C. And so this is going to be increase the temperature of 1 kilogram of a substance by 1 degree C. So if you're not already familiar with that definition, then this is your opportunity to make some notes on it and then get it when it comes up in your exam. The beaker was filled with 0.2 kilograms of 25 degree liquid water and placed over a Bunsen burner. The temperature of the water in the beaker increased to 100 degrees C. Here we're asked to calculate the total energy required to increase the temperature of the water in the beaker from 25 degrees C to 100 degrees C. And we're asked to give our answer in kilojoules. So, in order to answer this question, we need to use the equation that states that energy transferred is equal to the mass times by the specific heat capacity times by the change in temperature. And so in order to answer this then, we need to identify what is that change in temperature, what is the mass, and what is the specific heat capacity. Well, first things first here, we can see that the mass is 0.2 kilograms. Now for the specific heat capacity, we need to remind ourselves of the table on the previous page. Now here we're talking about liquid water, which we decided was what Y is. And so we have a specific heat capacity, 4,186. Now we need that change in temperature. So because it went from 25 to 100, the change in temperature is 100 minus 25. So if we put everything now into our equation, energy equals 0.2 times 4,186, and then times by that change in temperature, which is 75. Now, popping that into the calculator now, I get 62,790 joules. However, this question is asking for the answer in kilojoules, isn't it? So we need to know that we can convert from joules to kilojoules simply by dividing through by 1,000. And so that's exactly what we do here. And we get 62.79 kilojoules. This question is about the motion of a train between two stations. Identify which of the following statements about speed and velocity is correct. Now looking at these options, I can see that the first and second one is talking about vectors versus scalars. So I think it's worthwhile we just talk about quickly what the difference is between a vector and a scalar. So a scalar is a quantity, only has magnitude. So it doesn't have any direction to it. Whereas a vector has both magnitude and direction. And what that means is it matters if you're going left or right or up and down. It's not just a case of, oh, I've got a speed of 5 meters per second. I mean, that will still be its velocity, but the velocity will be, I have a velocity of 5 meters per second to the left or to the right. Anything where you can represent it with an arrow. So having a look at this now, I should know that velocity is the vector of them both. And the great thing is about speed versus velocity. Speed begins with an S, it's a scalar, and velocity begins with a V, is a vector. So actually those two are kind of gifts to you really. They're the perfect examples to learn if you need to have one example in your arsenal for when the exams come up. So actually, without looking at the others, I can see that velocity is a vector is my correct answer, so I tick that fourth box. If we look at the others though, just to explain it, speed is always the same as velocity. That's not true because although the number part will be the same, it could be negative if you had velocity, for instance, if you were going backwards. Whereas if you were just looking at the speed, you don't care that you're going backwards, it would just be the number. Whereas the third point, velocity is measured in meters per second squared. No, velocity is measured in meters per second, no squared. It's acceleration that is measured in meters per second squared. So there we have it, velocity is a vector. Now we're asked to draw lines to identify whether the measurements are vector or scalar quantities. So these are just bits that we need to have memorised really, okay? So we need to know that distance is an example of a scalar. So distance just tells us how far we've gone, but it doesn't tell us in what direction. Displacement, on the other hand, is the vector version of distance because it does tell us if we went backwards, forwards, left, right, east, west, north, south. And acceleration is also a vector. And that's because you can accelerate and you can decelerate. You could go faster or you can be slowing down. So those are our answers to this question. If you don't know them, then make a note of all those facts and get memorising them because they should all be easy marks in the exam. So now we're told that train X was travelling between two stations, station E and station B. Train X was stationary at station A. It then increased its speed to 50 metres per second over the next 40 seconds. So then the train continued its journey at a constant velocity for 1.5 minutes before decelerating for 30 seconds until it stopped at station B. So here we're asked to assume the train had constant acceleration and deceleration, and we're asked to complete the velocity time graph. So the first thing to look at is the fact that once it gets to this 50 metres per second, it has a constant velocity for 1.5 minutes. Now if you look here at the x-axis, it's in seconds. So we need to know that 1.5 minutes is equal to 90 seconds. If you don't know that straight away, then you can just multiply it through by 60 in your calculator and you'd get 90 seconds. So as we left off at 40 seconds, if we add 90 to that 40, we know that we're going to stay at a constant velocity until we reach 130 seconds. So there we have it. So then we're told before decelerating for 30 seconds until it stopped at station B. So it's going to come to a stop, so it's going to end with a velocity of 0 and it's decelerating for 30 seconds. So at the minute we are at 130 seconds, and if we're going to decelerate for 30 more seconds, we're going to come to a stop at 160 seconds. So that means we're going to do a straight line, use a ruler and a pencil with this question in the exam, a straight line down to 160. And so there we have it, that is our completed velocity time graph. The line between t equals 0 seconds and t equals 40 seconds has a constant gradient. Explain what this constant gradient indicates about the motion of the train between t equals 0 seconds and t equals 40 seconds. So let's have a think, one at a time, of what these would all look like on a velocity time graph. So this first point here, the train is travelling at a constant velocity. That would just be a horizontal line, and that isn't what it looks like, so it can't be that. So the second point, the train speed is decreasing. That means that over time velocity must get less. And again, it didn't look like that. However, if the train's velocity was increasing at a constant rate, you would get this straight line, and so that is correct. But let's look at this last point as well. The train is stationary. That would just be another horizontal line, but this time at 0. Okay, so next up we're asked to calculate the acceleration of the train in the first 40 seconds. So let us remind ourselves then of what the graph looks like, because we're going to need to use that to calculate this. So there's two ways we could do this. The way that I would recommend that you do this is by using the gradient. We should recognise that the acceleration of a velocity time graph is found by calculating the gradient of the line. So before we do anything, let us just remind ourselves of the equation for the gradient. This comes up in all your sciences and maths. We need to know that gradient is equal to the change in y over the change in x. Or we might have learnt it as the rise over run. But here what I'll do is I'm going to change this into a little bit of a triangle here. Okay, so we've got 50 and 0. I can see that the change in y will be 50 minus 0. Then on the x-axis, I can see the change is 40 minus 0. So putting that into the calculator, I get a gradient and therefore an acceleration of 1.25 metres per second squared. As the train left station B from rest, it accelerated at 4.5 metres per second until it reached a velocity of 60 metres per second. Calculate the distance travelled by the train. So to do this, let's just think about what quantities we know. So here we've got initial velocity is 0 metres per second because it started from rest. The acceleration we're told is 4.5 metres per second squared. And we're told that it ends up, so it has a final velocity of 60 metres per second. And of course, we need to get the distance travelled by this train. So that there is our question mark. So looking at this, we should recognise the correct equation to use, okay? So the formula we must use states that the final velocity squared minus the initial velocity squared is equal to 2 times the acceleration times by the distance. So you can see me writing it here. So of course we need to find the distance and we know the other quantities. So what I would do here is just substitute those values in. So that leaves me then with 60 squared for the final velocity squared minus 0 squared. And then that's going to be equal to 2 times the acceleration, which is 4.5, times by the distance, which is of course our unknown. So if I simplify this now, and if I do 60 squared minus 0 squared in my calculator, I get 3,600. 2 times 4.5 times distance then becomes just 9 times distance. And rearranging this to get the distance on its own, we need to divide through by that factor of 9. So we're going to do 3,600 divided by 9, which gives us 400 metres. In this question, it was assumed that the acceleration of train X was constant. In reality, the train's acceleration decreases as the velocity of the train increases. Here we're asked to complete the sentences to explain why. Okay, so here we're told as the train's velocity increases, air resistance, and we should know that as we go faster, the air is hitting us more rapidly, and therefore air resistance increases. Now the effect of this is going to decrease the resultant force on the train. Of course, it's got that thrust pushing it forwards, but now it's got this air resistance counteracting that and making the overall force on the train less. So now it says force is proportional to acceleration. So because that resultant force has decreased, the acceleration will do the same because it's proportional, and it will also decrease. Light-emitting diodes have many uses. They're used in many electrical devices, including remote controls and traffic lights. Here we're asked to identify the statement that describes a diode. And this really is just going to test that we know what they are, okay? So we should know that a diode is a component which only lets current flow in one direction. So if you didn't know that, stop the video for a minute and make a note of that now. If we look through some of these others here, a component which measures current in a circuit is an ammeter, so not a diode. And a light-dependent resistor is just called a light-dependent resistor, or an LDR. And a temperature-dependent resistor is called a thermistor. However, the diode is a component which only lets current flow in one direction. Now we're asked to circle the correct circuit symbol for a diode. So we should know that a diode is this one. So the circle surrounding it you may or may not see, but what you will always see is that triangle with a line at the end of it, at the end of its point. To run you through these others, just so you know, this first diagram here shows a bulb. This diagram underneath the bulb shows a light-dependent resistor. The fact that we've got this rectangle there shows it's a resistor, and the arrows pointing towards it show it's light-dependent. And this final one here is called a thermistor. So this is what the temperature-dependent resistor looks like. So again, if you're not familiar with each of those and what they are, then stop the video for a minute and make a note on it now. Okay, so now we're asked to complete the flowchart to show the energy transfer that occurs in an LED when it's connected to a circuit with a power supply. So we should know when it's connected to that power supply, it receives electrical energy. And when we turn on that LED, it's a light-emitting diode. And that means that that electrical energy is getting transferred to light energy. So that is the energy transfer that occurs in an LED when it's connected to a circuit with a power supply. Now we're asked to circle the IV graph for a light-emitting diode. Well, this is another memory question. We do need to be able to identify and even sketch these different graphs for a few different components. So remember that a light-emitting diode is just a diode that happens to emit light, okay? It's still a diode. And we know that diodes only let current flow in one direction. Now, this is actually to be seen on these graphs. Because here, can you see that there's no current flowing here? Only in this direction. All of the other ones have current flowing in both directions. It just happens to be negative, which means it's flowing in the other direction. So therefore, even if we didn't have this memorised, but we knew what a diode was, a component which only lets current flow in one direction, we could indeed still identify the IV graph for a light-emitting diode or any diode is this one here. So here we have a big 6-mark question. We're asked to describe an experiment that will find the IV graph of a light-emitting diode. And we can use a circuit diagram in our answer, and I think they're a really useful way to aid our explanation. So let's start off by drawing our circuit diagram. Now, the first thing I'm drawing is the symbol for a light-emitting diode. So what we have here is this triangle with a line against it with 2 arrows pointing away. That's because it's a light-emitting diode. A diode alone wouldn't have those arrows. Then we have that diode connected in series with a power supply and also an ammeter. Then we're going to place a voltmeter in parallel. Now, the reason why we have that ammeter is to measure the current in this experiment. And we always want to have ammeters in series with the component that we're measuring. So then we also have a voltmeter, which is the circle with the V in it. Now, voltmeters always need to go in parallel with the component that we're investigating. And the whole point of a voltmeter is to measure the potential difference or the voltage in the circuit. So there's one last thing that we need to add to this circuit diagram that we're missing at the moment. So we need to have a way to vary the potential difference. And the way that we're going to do that is by adding a variable resistor. A variable resistor looks like a rectangle with a diagonal arrow going through it. So now we've got this circuit diagram set up, and by drawing it and labelling it well, already actually we've got quite a good chunk of these marks in this question. So now let's describe what we're going to do. So once we've set up the apparatus in this way, we're going to record the potential difference and the current. Once we've done that, we're now going to use our variable resistor to change the potential difference. Once we've done that, we're now again going to record the new potential difference in current. Again, we're going to use our voltmeter to measure the potential difference, and we're going to use the ammeter to measure the current. Now we're going to use that keyword that we use in so many of these investigation questions. We're going to repeat this process. Because the more we repeat it for slightly different potential differences, the more data points we'll have for our graph. Now, once we've done this, we'll notice that we're only getting positive potential differences. So we're only really getting half the graph. What we need to do now is reverse the power supply. By reversing the power supply, we're now going to get negative potential differences. And now we're going to repeat the process before of recording the potential difference and the current, and then using the variable resistor to change the potential difference and repeat. So once we've done this now, we're going to have many data points for both positive potential difference and negative potential difference. So now all we need to do is plot a graph of current against potential difference. And this, of course, was the aim of the game. When we go back to the question to reread it to check that we've got everything down, you can see that we were asked to describe an experiment that would find the IV graph of a light-emitting diode. We've done that here. So you see there's a lot of points we can say here. In these 6-mark questions, we don't want to limit ourselves just to saying 6 points. In any other question, that's a fine method, but these 6-mark questions, instead we're being marked slightly differently. We need to make sure that we give as full an answer as possible and not just giving a few points that we'll do at the beginning of the experiment. We make sure that we talk our whole way through from the beginning, the middle and the end of this experiment, and we talk about any apparatus and measurements that we need to take. So there we are. This would be our perfect model answer. This is a very common question, so by all means, get writing this down and get learning this. Decorative garden lights are arranged in a series circuit. Here we're asked to give an advantage of arranging these lights in a series circuit. So we should know that a great thing about series circuits is that you only need to do one switch and everything will turn on at the same time. So that is a definite advantage to these, because otherwise imagine going around your garden or your Christmas tree turning on every light one at a time. Won't be suitable, will it? So that's a great reason why series circuits suit this. So now we need to give a disadvantage of arranging these lights in a series circuit. Now, this is like the flip side of what we just said. The problem is if one light breaks, then you've broken that circuit and none of the other lights will turn on either. So that is our disadvantage. So now we have a battery with a potential difference of 12 volts. It's connected to a series of 2 lights of equal resistance. The resistance of each light is 24 ohms, and we're asked to calculate the total resistance in this circuit. So we should know that in series, the total resistance is just equal to the sum of the resistances. So in this case, the total resistance will be equal to 24 plus 24. So that gives us a total resistance of 48 ohms. Next up, we have a recall question. We're asked to identify the definition of current. So we just need to know this definition, so if you don't know it, time for a flashcard. The current is known as the rate of flow of charge. So that's a nice easy thing to remember to get some easy marks. So next up, we're asked to calculate the current in the circuit. So to be able to work this out, we need to know which formula to use. At the minute, we know that the voltage is 12 volts, we were told that earlier, and we worked out that the total resistance in this circuit was 48 ohms. So that means that we need an equation with potential difference in it, with total resistance in it, and with current in it. So here we have potential difference equals current times resistance. Or you might know that equation as V equals I times R. Both of them mean the exact same thing. So here we need to get the current though, don't we? So we're going to need to rearrange our equation to get current as the subject. So here we've got current equals potential difference, and then we need to divide by that resistance, doing the opposite of the multiplying, to get the current on its own. So in this case, that gives us 12 over 48, which gives us the current equal to 0.25 amps. An investigation was carried out to find how the number of turns on a coil affects the strength of an electromagnet. A wire was wrapped around a large iron nail, and the wire was connected to a battery, as you can see in this diagram. This formed an electromagnet. The number of paper clips that the electromagnet would pick up was recorded, and the number of turns around the iron nail was increased, and the method repeated. Here we're asked to complete the sentences, using the word in the box to help you. Here we're told that when a current flows through a conducting wire, a something field forms around the wire. So we need to know that whenever we have a conducting wire that has current flowing through it, we have a magnetic field forming around the wire. So that is our first word here, and we can cross that out. So the strength of the field is dependent on the something through the wire and the something from the wire. So we need to think, what is going to affect how strong this magnetic field actually is when it's got a current running through it? Well, one of those things is going to be the size of the current that runs through it. So if we have a bigger current, we will make a stronger magnetic field. So the second point is going to be the distance from the wire. So the closer we are to that wire, the stronger the magnetic field. As we move farther away, it's going to get slightly weaker as we move away until eventually we won't be able to experience a magnetic field at all. So there are our key points there. They are perfect really for making a flashcard or some notes from. So if you didn't know these facts, then just pause the video for a minute and get those down. A simplified diagram of the electromagnet is shown below. Here we're asked to draw the magnetic field pattern around the electromagnet. So here is the diagram that you need to draw. Now the key features that we need to include in this question. One of them is that the magnetic field lines have to point from north to south, and that's always the case. We should also know that the magnetic field lines are never going to cross each other. That will never happen. And it's also worthwhile knowing that the closer together the lines, the stronger the magnetic field. So as it's like leaving the ends of this electromagnet, you can see that the lines are closer together, and that's where the magnetic field will be stronger. So this is the general shape that you need to know. The magnetic field pattern around an electromagnet is exactly the same around a bar magnet. So if you learn it once, you know it both times. The results were plotted on a graph. Here we're asked to draw a line of best fit. So to do this, we need to get our ruler out and a pencil, and we need to line up our ruler across the dots so that roughly the same amount of spots are above our ruler as below it. Now this will never be perfect. I won't be able to do it perfect, and you won't be able to do it perfect unless we were computers, but we'll do it our best and use a pencil to draw a line of best fit. If you decide it's a really bad one, you can always just rub it out and start again. But here we have our line of best fit. So now we want to predict how many turns on the coil would be required to pick up 5 paper clips. So to do this, we want to go to our line of best fit, and I can see 5 is here on the y-axis. And I'm going to use my ruler to draw a horizontal line across from 5 all the way up to the line that I have drawn. And then I will draw a vertical line leading downwards. Now make sure that you use a ruler here, because that is going to be important to make sure that you get a nice straight line and our answer is as close to what we need as possible. So this one here was a multiple choice. We've got some options. So 102, nope, it's clearly not that. I can see it looks somewhere slightly below 130. So 126 is the next option, and that does appear to be correct. Next up, 98, nope, 109, nope. So I definitely think 126 looks like our answer here. So now we're asked to explain the relationship observed between the number of turns on the coil and the number of paper clips. So obviously we can see as we have more turns, we can pick up more paper clips, but here we need to explain it and give the science. So what we should know is that more turns induces a stronger magnetic field. And therefore that causes us to have a stronger force of attraction. And this is going to be why we can pick up more paper clips as we have more turns on the coil. And that there is our explanation for why, as the number of turns increases, the number of paper clips it can pick up also increases. So now we're asked to suggest how the reliability of the experiment could be improved. And whenever we see that question here in any experiment where we're asked how can reliability be improved, we want to say that we need to do repeats. And that is something that will repeat across all of your sciences, and any experiment that happens, that will always be a good answer. A person is using a wheelbarrow as a lever to transport a load of mass 20 kilograms. Told the weight of the wheelbarrow is 90 newtons and the person used an effort force of F to lift the wheelbarrow. Here we need to calculate the weight X of the load. Now let's think about what we know about this load X. We know that it has a mass of 20 kilograms, and we also know that the formula for weight is that weight equals mass times by gravitational field strength. Well, looking at that, we have all of the information that we need to calculate the weight. We know that the mass is 20, and we're told that the gravitational field strength is 10. So weight is 20 times by 10, which gives us 200 newtons. So now we're asked to calculate the size of the moment caused by the weight of the wheelbarrow. Well, to answer this, let's first remind ourselves of how we calculate moments. So we need to know that the equation for moment is that moments equals force multiplied by the distance normal to the force. And when we say normal to the force, that means at right angles to the force, which is what we have here. So looking here, we're looking at the weight of the wheelbarrow and what moment is caused by that. That weight is 90 newtons, and that distance at right angles to that force, to the pivot, is 0.5. And so 90 times by 0.5 gives us 45 Newton meters. And that there is our answer. So now we need to complete the sentence by circling the correct word. We need to say what the direction of that moment is. So the moment caused by the weight of the wheelbarrow is... And if you imagine here that the wheel is the pivot in this example, that 90 Newton force is going to push down and it's going to end up making the wheelbarrow turn in a clockwise direction. Whenever I'm doing these, I like to just get out a pencil or my pen, and in this case I would pinch together one end of my pen, the left end of my pen, with my thumb and my forefinger of my left hand, and I would like to imagine that I've got this weight acting down on it. So what I'm going to do is I'm going to push my pen down on the right end with my right hand, and I'm going to see what happens to that pen. And what I'll notice is it will start to rotate in that clockwise direction. And that is exactly what we need to do here to work this out. So in this case, like we said before, that the moment caused by the weight is going to be in that clockwise direction. So if you ever feel a bit stuck or confused, just get out your pen and try and model the situation using your pen and your fingers. So now we're asked to complete the sentences about the law of moments. So here we're told, if an object is something, the total clockwise moment is equal to the something moment. So here the answer is going to be balanced. If an object is balanced. Alternatively, we could have said in equilibrium, but of course that is what is in the box here. So if an object is balanced, the total clockwise moment is equal to the anti-clockwise moment. And that is going to be our little definition there. That is the law of moments. So if you're not familiar with that law, do stop for a moment and make a note of this law, because this is a really important fact that will be easy marks in your exam. The total clockwise moment is 105 Newton meters. Given that the wheelbarrow is in equilibrium, calculate the effort force F required to lift the wheelbarrow. So we've just said, haven't we, that if the system is balanced or in equilibrium, the clockwise moments are equal to the anti-clockwise moments. Well, we know that the total clockwise moment is 105 Newton meters. We need to work out then what the anti-clockwise moment is and set it equal to that. Now we know that moment equals force times by the distance normal to that force, or at right angles to it. So, like we said here, we know that the total clockwise moments are going to be equal to the total anti-clockwise moments. So because in this question we've been told what the total clockwise moment is, we therefore know what the total anti-clockwise moments are. And there's only one anti-clockwise moment in this situation here. And that is the moment caused by this person lifting up the wheelbarrow. So that means that we can say that that 105 is equal to F, force, that effort force, times by that distance between that person and the pivot at right angles to the force. So that's 1.2. So if we then substitute those in, then we've got the 105 equals F times by 1.2. So this is something that we can now rearrange. We can say that F equals 105 divided by 1.2. And that gives us 87.5 newtons. And that is the effort force F required to lift the wheelbarrow. All charged particles and objects have electric fields around them. Here we're asked to identify the description of an electric field, and this is a little definition that we just need to know. So we should recognise that an electric field is a region where charged particles experience a force. So the answer to this one here is our first box, a region where charges experience a force. The diagram below shows a negative particle. Here we're asked to circle the diagram which represents the electric field around the negative particle. Well, we should know that when we have an electric field, it will go from a positive charge to a negative charge. We should also recognise that it's going to be a radial pattern, so it's going to be arrows either going towards this spherical charge or away from it. It's not going to look like the two options on our right with these circles circling around the charges, so we can cancel these out straight away. And using the fact that electric fields go from positive to negative, we can then positively identify our answer as this one here. And that's due to its general shape and also the fact that those arrows are pointing towards the negative. Electric fields are responsible for the effects of static electricity. Static electricity has many useful applications. Static electricity is used to spray an even coat of paint onto cars. The car is connected to a negative electrode and the paint spray is connected to a positive electrode. Here we're asked to complete the sentences to explain how this ensures the car is evenly sprayed with paint. And we are to use the words in the box to help us. So it starts, paint particles all have, and if you look at the diagram here, you can see it's connected to a positive electrode. As a result, we can say that paint particles all have a positive charge. Now, because they're all going to have a positive charge, and we should know that like charges repel, the paint particles will repel each other. This means the paint particles something and gives an even coat. Well, as they're all repelling each other, they're going to spread out, and that's what gives it that even coat. So now onto the car. The car has and again, we need to look at the diagram here. I can see that the car is connected to a negative electrode here. So I'm going to say that the car has a negative charge. And this is the something charge to the paint. Well, it's the opposite charge to the paint. And that's really important because the fact that the car is the opposite charge to the paint means that it's going to get attracted. So we're going to say that the paint is attracted to the car. And this ensures that the back of the car gets painted.
Well done for making it to the end of this paper, lovelies. I'm really, really proud of all of your hard work.